Hello. Is the mic on?
Not really.
Probably we want it. I can also speak up. I don't mind.
Is this being streamed?
That's what I'm not sure about. Should I start?
Yes.
Okay, I'll get started. Great. Yeah. Hi everyone. My name's Stephen Holtzen. I'm here to give the session overview for machine and automata learning. So let's just dive right into it. So machine learning at a high level, what is it? It's a means for using data to describe intent to the computer. I think this is like a good summary. It's kind of a way of capturing what connects a lot of the methods in this session, right? So I'll give you kind of a caricature of what I think of machine learning as. So you start with kind of the world, and from the world you're going to extract things from it, right? So in this case, maybe I got a bunch of images of cats and dogs, and I collected them together, right? And I'm going to call that a data set, right? That's going to be kind of an important ingredient in this setup, right? And then from this data set, I'm going to do something called learning, and we're going to have different notions of learning. We're going to have different ways of collecting the data set, and there may be different loops in this cycle, but this is kind of your high-level kind of picture of what to have in your mind, right? And then from that learning process, we're going to get something called a model, right? And this model is going to have data as part of it. That's going to be part of how you get it. And then once you have this model, I'm going to take another thing from the world, like for instance an image, in this case an image of a cat. I'm going to plug that into the model, and then the model might tell me that's a cat, right? So this is kind of the picture in your mind of what machine learning is trying to accomplish. And I think the important thing to take away from this is that, good luck writing a program that can do this. Right? It's very, very hard sometimes to do stuff without this kind of data-driven approach, right? Very difficult. So the data is really a useful kind of way of expressing intent to the computer in this way, right? Because it's telling us, here's the essence of what a cat is. I'll give you many, many examples, and then it'll figure out, for you how to do this classification, right? So I think kind of, I don't know what happened to my slides, but, an exciting theme I wanted to point out here is that, and this is something I think each of the 4 talks in this session is going to explore, is, how do programming language solutions connect to, apply to, and solve interesting core machine learning problems? I think this is a really interesting thing because, I think we have, I don't know if anyone went to Nate's awesome keynote this morning about how, in networking, by connecting up ideas from programming languages, we were able to come up with really interesting and compelling solutions to problems that they had in networking. I think we're starting to poke at and prod at similar things happening in machine learning as well, and I think you can come to this session and sort of see what that's all about, right? Oh, something very bad happened to my slides. Okay, anyway. So here are some of the big challenges happening right now in machine learning that I want to mention, and kind of how each paper connects up to one of those challenges, right? So one big challenge in machine learning is we want flexibility in describing that model, right? So on the previous slide, I had this model here. What is that? How do I tell you what that is? That tells me what I should be learning, right? So this first paper in the talk, Efficient Shad, is going to give us kind of a very interesting and technical way of getting flexibility in the model via differentiable programming, right? And differentiable programming is a very interesting and technical idea, but it's been incredibly successful, and I'm going to talk a little bit about that after this, about this overview. So the model might learn unsafe behavior. This is a big, big problem right now in machine learning. Like it might, you want to use your model for a self-driving car. The car needs to not run off the road. You need to be able to make sure that your machine learning model won't predict something that's unsafe, right? So this is where some of the ideas from program verification start to come to the fore and help us with some of these big problems in machine learning. And we're going to talk a little bit about how ideas from abstract interpretation kind of connect up to this goal of getting safe machine learning. Right? Another big challenge. We might need too much data to learn a good model, right? So I gave you this model, I gave you these pictures. You might need way too many pictures, right? And the model might still learn something you don't like. So how do we give it even more structure? How do we give it an even stronger, what you would call an inductive bias, to figure out what should it be learning, right? And that's where this cool paper, Programming by Demonstration for Long Horizon Robot Tasks, kind of comes in, right? So they're going to use kind of programming languages to kind of they're going to do program synthesis to kind of figure out what the model ought to be, and then they kind of combine that with a refinement loop with the language model. It's a very interesting paper. And then finally, we may want to learn exact functions, right? This was my way of connecting up these things to automata learning, which is a slightly different kind of approach, right? It's coming from a different school of thought, but I think it's interesting, and it falls under this general theme of using data to describe what programs do, right? And it's going to be very different. But I also think maybe it's, I think it's super interesting and exciting. I'll try to give you a little overview of that at the end, right? And that's on learning, sorry, I covered it up, on learning polynomial. I can't read the whole title here. Sorry about that. We'll get there. I'll show you the title. Don't worry. All right, great. So machine learning is all about minimizing loss. I'm going to talk about the first paper first, talk a little bit about differentiable programming, right? So I'm going to give you kind of this input training set. I'm going to run each image through the classifier, and it'll tell me a bunch of labels, right? It'll say that's a cat, that's a dog, that's a cat, that's a dog. And you can look at this and say, okay, well, some of these are not correct, right? That's probably not a cat, et cetera. So I can count up how many of those are wrong, and that's called my loss. The loss is kind of the most important thing, the most important semantic object in machine learning. It's how far your model that you're learning is from the thing that you want to learn. So it's a distance metric. Right? And you can come up with different kinds of losses. They'll have different properties, but really it's just how far you are from the thing you want to learn. Right? And in this case, we can write down a little formula for our loss. The loss of the data set, and then the parameter theta is kind of floating around in there. That's just the sum total of how many predicted labels were different from true labels. Right? So it's a function. It's in terms of theta. And the idea is that we want to differentiate this with respect to theta. We're going to turn this into an optimization problem. Right? This is like a standard machine learning kind of pipeline. I have a loss, which is how far I am from the thing I want to be able to predict. And then I'm going to differentiate this loss with respect to the parameters and then search that space to kind of optimize my function. So you can imagine your loss surface kind of looks squiggly and you would want to move along the tangent to that line. We're going to do that with gradient descent. Right? So I want flexibility to describe f, this classification function and the loss, and manually differentiating is cumbersome, right? I don't want to be manually differentiating. I don't want to manually write the derivative code. And, I have fairly large spectrums of models that I want to write that have a lot of structure in them. And the models are getting more and more structured over time, right? So a solution to this is automatic differentiation, which is in fact a program transformation. I think this is something that's really exciting that's started to be kind of internalized within the programming languages community, is that automatic differentiation is in fact taking a program, translating it into a new program that computes the derivative of that program. Right? And this is a cool idea. It's something that programming languages people can really get into. So you can describe your program over here in kind of Python code. This is like the very successful automatic differentiation setup called JAX. And you can check out this great blog post, the num.at/autodiff, which kind of walks you through building your own autodiff. I really like that blog post. But anyway, what are the PL challenges? Well, correctness. We want to formally verify that the transform program computes the correct derivative in the presence of interesting program constructs, like higher order functions and so on. Efficiency. We want to make sure that autodiff computes, ideally computes the derivatives on the order of running the program. That's kind of the gold standard. If you can get there, you're very happy. Right? And hopefully parallelism too. Maybe I want to compute lots of derivatives at the same time, right? And then in that case, I would like to run them in parallel, maybe even amortize over the different parallel runs that share sub-computation trees. So this paper, Efficient SHAD, is a step in connecting the theory of automatic differentiation. Sorry? 2 minutes, okay. In particular, the formally well-understood SHAD algorithm to an efficient implementation, so kind of proving efficiency, right? So I'm going to fly now, right? Hopefully this slide is enough for you to kind of get excited and want to come to this section. But the next one, verifying machine learning systems, you want to have safety. So I showed you already that deep neural networks, you can write them as a function, right? Which just takes input features to an output label. And one of the ideas in making these things safe is we want to use abstractions to kind of over-approximate the behavior of the neural network and show that if that over-approximation doesn't contain unsafe behavior, then we're happy, right? So this paper, I'm just going to fly at this point. So this paper kind of gives you a new and cool way of designing an abstraction for this neural network verification problem that's tighter and has better scalability than existing ways. And this is a really tricky problem. I mean, people have been working very, very hard to come up with the right abstract domain for neural networks so that these things can scale to reasonable things. It's like it's a very challenging climb, right? And I think this paper is doing something pretty cool where they're kind of very tightly approximating the behavior of the neural network on the discontinuities around the origin, which is nice stuff. So kind of. This one is about, the setting that it's in is very cool. So what is inductive bias? So inductive bias, we want to generalize beyond the data set and have data efficiency, right? So inductive bias kind of helps us learn more efficiently. It's kind of like you're telling the model what should you look like, right? You're giving it more structure. You don't want to just have unstructured network, right? So this paper is using a programming language to give an inductive bias for learning. I'll leave it at that. It's very cool. Come check it out during the session if you want to learn more. And then finally, we have a really nice paper on automata learning, where you have this automata learning setting, which is kind of different, where you're assuming that there's a hidden automata inside the world, and you're allowed to kind of query that automata, that hidden automata, to figure out if certain strings belong to it. And the goal is to reverse engineer what kind of automata that is, right, just by observing this input-output behavior. And they came up with a way of going beyond deterministic finite automata. So with that, that's kind of what's happening in this session. I hope you'll come by and learn more, because this is all I had time. Thank you.